You're all here. So the audience is here. I'll call a metric space complete if it satisfies the condition that every Cauchy sequence of elements of X converge. Now, that theorem has two words that we haven't defined yet. What does it mean for a sequence of points in a metric space to converge? What does it mean for a sequence of points in a metric space to be Cauchy? And let's see if we can't just think about it to figure it out. So, a metric space is complete if it satisfies the conclusion that Cauchy sequences converge. Let's go back to Rn and then we'll translate. So, what does it mean for a sequence of real numbers to converge?
For all epsilon greater than 0, there exists an n in the natural state.
Well, I'm just writing down like statement. Well, I'm going to say that real numbers converges to X in Rn norms. Okay, now say it.
For all epsilon greater than 0, there exists a big N in the naturals, such that for all little n greater than big N, the absolute value of X minus the little n term of the sequence less than epsilon?
No. Now, if I want to translate this to a metric space, I don't know how to subtract elements of a metric space. I just know how to measure distance between them. But that seems like just fine, right? Because what's the point of the absolute value of x minus xn? Yeah, that is the distance. So if I want a definition of convergence in a metric space, that's the only change I need to make. Let xd be a metric space. Let xn be a sequence of elements of x, also known as a function from the natural numbers to x. I say that xn converges to some little x in big X if, for all epsilon bigger than 0, there exists a big N such that for all little n bigger than big N, absolute value of x sub n might, nope, the distance from x sub n to x is less than epsilon. That seems pretty okay? And we have a few examples of metric spaces. I think I want to focus on this one. Let's focus on Rn. All right, so we checked that that's a metric space with respect to the L2 metric. And if completeness is supposed to somehow mean that like it's got no holes in it, then Rn doesn't seem to have any like holes in it, whatever that means. So it better be complete. But let's maybe first things first. Let's just decide what it means for a sequence of elements of Rn to converge. And maybe let's even just write it down this way. So I claim that there is a version of convergence, a statement of convergence of points in Rn that just depends on the individual components of an n-tuple. So if I have a bunch of things that look like, let's just do it in R2. So there's a sequence of elements in R2. Let's suppose that xn, yn converges to some point x, y. Do you think that should mean that xn should converge to x and yn should converge to y? That seems reasonable. If this xn converged to like x plus 5, then xn yn would be getting close to x plus 5 comma something. So the following proposition says exactly that. Suppose that xk, k equals 1 to infinity. So I've included this just to let you know what the parameter in the sequence is a sequence of elements of Rn with respect to the L2 metric. And let's suppose that each xk, right, is an n-tuple. So each xk is x1, x1k, x2k, all the way on up to xn sub k. let's let x be an element of our n, so it's got, it's a list of numbers. The sequence x sub k converges to x if and only if for each I, that sequence of real numbers converges to x upper I. So a sequence of elements of our n converges to a point if and only if each of the values converge to the point. That seems believable, but I think we should probably prove it. And this will be a good just illustration of how to prove things converge in a metric space. So this is an if and only if, so I guess we have to go both ways. Let's let this be a sequence of elements Rn. It's given by a bunch of sequences in each of the terms in xk. Let x upper 1 be an element of Rn. Suppose that for each I, this sequence converges to x upper I. And I want to prove something about convergence, so I need to show that for every epsilon bigger than 0, there exists a big N such that some stuff happens. So just as in our semester analysis, we should consider any epsilon bigger than 0. Now I need to come up with a big N. And what is the one thing that I've assumed about this sequence that might get me some big N's? Convergence. Convergence. So since for each choice of I, this converges, that means for each choice of I, we get a choice of big N. So let's just list each one of them. There's some N, so for each choice of I, that sequence converges to x upper I by assumption. Thus, there is some big Ni such that for all, I'm going to say little k because this sequence has little k being its independent variable. For a little k bigger than big N sub I, absolute value of x upper I sub k minus x upper I is less than, and I'll put an epsilon there. So there are a bunch of red marks that are just like random typos, but that red epsilon is because I'm probably going to need to divide it by something. Everyone happy enough right now? And whenever you just see like a bunch of choices of big N, what should you always do?
Take the max.
Right, if you see a bunch of deltas, deltas are supposed to be little, so you should take the littlest one. If you see a bunch of big N's, well, big N's are supposed to be big, so you should take the biggest one. Let's consider any little k bigger than big N. Well, since little k is bigger than big N is bigger than or equal to n sub I, this statement, the conclusion of this statement holds. So the difference between x sub k upper I and x upper I is less than epsilon. But again, like that's this red epsilon that I'll want to do something with. So let's just hold on to that for a second. And let's see, we can keep on going through the proof just as is. But if you want to just like write a proof from scratch, you wouldn't start it this way. Let's actually just figure out how the proof should go and what we need to divide that epsilon by in advance. So let's figure out what should go there. So what is it that we want to show if we want to show that the sequence converges? Or we want to show some distance is small, right? And you know what? Yeah, let's actually have this being recorded. So what is it that we want to show? So we want to show for every little k bigger than big N, the distance from x upper k? No, x lower k. To x is less than epsilon. That's what we want. What's the definition of the distance between 2 points in Rn? If you're using the L2 metric. Of?
That was all I was doing.
It's sort of the sum of every x term from so x minus xi, that all squared.
So So that's still what we want to show, but let's just mess around with this and simplify it. This isn't going to be the proof. This is going to be like the proof backwards. What would you want to do if you wanted to simplify that?
Square both sides.
Square both sides.
Square both sides. Should say divide both sides.
No, multiply both sides by 0 would be very simple.
But that would be false.
Okay.
You're right. Would you take like a max bound on like the x k's minus the x i's?
Yeah, in fact, we have an explicit bound on each of them, right?
Yeah.
This k is bigger than all of the big n's. So all of those things in that sum are less than epsilon, I guess. Squared. And of course, right, at this point, that's silly, right? Because what is I equals 1 up to n? You have an inequality like that. What can you tell me about, like, what is this equal to?
And times epsilon squared.
Is n times epsilon squared less than epsilon squared? Well, no, right? But what's the point? The point is that, like, this is the epsilon that we get to choose. So what do I really want that to be?
Epsilon. Square then.
Yeah, I think if I happen to have an epsilon over a root n there, I would be happy, right? So now we know how the argument's going to go. Oops, that's not what I want. So for each of these i's, this sequence converges to x up or I, and epsilon over root n is positive. So that means that there exists some big I such that for every little k bigger than big N sub I, that is less than epsilon over the square root of n. So if big N is the max of all of those things and little k is bigger than big N, then we get this conclusion. And, well, let's just chase back through this. So in order to go, well, this was just like equality, right? In order to go from there to there, that was a matter of all of these square terms were less than epsilon squareds. So if this is less than epsilon over root n, then xk upper I minus x upper I squared is less than epsilon squared over n. And now, well, you know what I was about to write. I'm going to write down the distance formula, and I'm going to do the walk that's on that blank sheet of paper. So the distance from xk to x, well, that's the square root of the sum from n I equals 1 up to n of xk upper I minus x upper I quantities squared. Well, that's less than the square root of the sum of each of those things is less than epsilon squared over n. But that's a sum that contains n terms. All of the terms are constant. So what is that sum equal to? Epsilon squared. And it's under a square root, so you know what's going to happen. What's the square root of epsilon squared? Epsilon. If epsilon were negative, that would be false, but epsilon is positive. If epsilon were negative, it would be absolute value of epsilon. Oh, nice. So did we start by considering any epsilon bigger than 0?
Yeah.
Did we then come up with a choice of big N?
Yeah.
Did we then consider any little k bigger than big N?
Yeah.
And conclude the distance from xk to x is less than epsilon?
Yeah.
Oh, as we have shown that for every epsilon bigger than 0, there exists a big N such that for all little k bigger than big N, the distance from xk, well, that's like a really bad mixture of notation. dxk minus x is not reasonable to write. Nice. So that's the proof that if each of the individual terms converge, then the n-tuple converges. Do you think the opposite should probably be true? I bet. So let's go the other way. Let's suppose that xk converges to x with respect to the L2 metric. Consider any epsilon bigger than 0. And we now know that there exists some big N such that for all little k bigger than big N, the distance from xk to x is less than epsilon. And maybe that epsilon will be divided by something. I don't know. Let's see what happens. Now we'll consider any of the i's from 1 to n and any k bigger than big N. Let's figure this out. So the distance told me something about square roots of squares. So maybe I'll start by taking advantage of the fact that absolute value is the square root of the square of the thing. Wow. So how does this differ from what the actual distance formula up there is? Like this is just a single thing and that's a sum of things? Are any of the things in that sum negative? So if I add some extra terms to the sum, the whole sum will become big O, right? So that's less than or equal to the square root of the sum from I equals 1 up to n of xki. Maybe this should be j. I kind of already has a job. And that final line, what is this blue thing equal to? That's the result of the distance formula. That's equal to the distance from xk to x. And what did I assume about that? It's less than epsilon. Since little k is bigger than big N. Hey, does that mean that each of the sequences x upon I converges to x upon I? Yeah, I think so. Neat. So let's now talk about what it means to be Cauchy. And you already know what I'm going to put here. Because what's the definition of, what does it mean for a sequence of real numbers to be Cauchy?
For all epsilon greater than 0, there exists a big old N is a natural, such that for all little m and n bigger than big N, the distance from the mth term to the nth term is less than epsilon.
Yeah. And you even translated to distance right there. So here's the definition that I'm going to put in this next line. Let xd be a metric space. Let xn be a sequence of elements of x. I say that xn is Cauchy if, for every epsilon bigger than 0, there exists a big N such that for all little n bigger than m and n bigger than big N, the distance from xn to xm is less than epsilon. And you'll remember that, like in real analysis 1, Math317, we proved that a sequence of real numbers is Cauchy if and only if it's complete. And one of the directions was easy, and one of the directions actually was kind of involved.
If and only if it's complete.
Converge.
Yeah, yeah. Sequence converges if and only if sequence is Cauchy. That's what we proved in real 1. And one of the directions actually used the fact that the real numbers are complete. The other one did not. And so let's do the easy thing first. No matter what metric space you're in, every convergent sequence will automatically be Cauchy. That will always happen. Let's prove it. Let's let x comma d be a metric space, xn be a convergent sequence of elements of x. Let's let x be its limit. So if I want to show that a sequence is Cauchy, I need to consider any epsilon bigger than 0. I need to come up with the choice of big N. Well, the only way that I have right now of coming up with the choice of big N is the fact that xn converges to x. So since xn converges to x, there exists some big N such that for all little n bigger than big N, the distance from x sub n to x is less than epsilon. And I guess that epsilon should be a red epsilon if I'm following the convention that I've been following. So I considered any epsilon bigger than 0. I came up with a choice of big N. Let's see if that choice of big N works. Let's consider any little m and little n bigger than big N. And let's try to measure the distance from xm to xn. And if you remember how we did this in real 1, we used the triangle inequality for absolute value. So maybe we'll use the triangle inequality right here. And, I mean, I guess that box line is written, but how do you come up with that? You say, well, the chalkboard will be my metric space. There is xn. There is xm. Can you think of a single element that's simultaneously close to xn and xm? What else? Right, since little n and little m are both bigger than big N, I know that this length is less than epsilon. I know that that length is less than epsilon, so what's the longest the distance from xn to xm could possibly be?
2 epsilon.
2 epsilon. So maybe you also know that we're going to divide an epsilon by 2. And that's exactly what we see right here. The distance from xn to xm is less than or equal to the distance from xm to x, plus the distance from xn to x. That's less than 2 epsilon, which is not equal to epsilon. So how should I fix the proof?
Divide all epsilons by 2.
I'll divide all 2 of the epsilons appearing so far by 2. Cool. So that sequence is Cauchy. So notice I didn't, like, there was nothing used that was fancy. I used the triangle inequality, and that's it. So it will be important when the converse happens. Let xd be a metric space. I'll say that xd is complete, or Cauchy complete, when I really want to emphasize that I'm thinking about Cauchy sequences converging and not some other notion of completeness. But Cauchy complete is all we'll talk about in this class anyway. If ever a Cauchy sequence of elements of x converges, and maybe one should emphasize to an element of x. But what would it mean to converge in a metric space if it converges to something that's not in that metric space? Maybe you have a bigger metric space that you're thinking about. Nice. So let's prove the thing that you're obviously expecting me to prove. Let's prove that the L2 metric on Rn is complete. And now maybe you even see where I'm going to use that proposition. So let's do it. So let's let xk be a Cauchy sequence of elements of Rn. I need to show that xk converges. And let's maybe even just plot out a course. So each of these xk's is xk above 1, xk above n. And I see n different sequences of real numbers. So let's try for this as a plan. I know that R is complete. So if I can show that each of these sequences is Cauchy, what can I conclude? What's true about Cauchy sequences of real numbers? They converge. So if I can get this, and I can give them a minute name. I can call it x up or I. If I could do that, can I just appeal to that proposition that we just proved? I think so. So let's do that. Let's try to show that each of these sequences, indexed by k, not by I, is Cauchy. Cool. For each k, xk is xk upper 1 all the way on to xk upper n. For some real number as that, I'll try to show that each of these is Cauchy. So how's it going to go? I need to show that for every epsilon there exists a big N such that for every, I mean, I don't want to use n because n is like the dimension of our n. So maybe, I don't know, I'll use k and l. I think that's probably what I do with the notes. So I'll use that. So the only place where I know to get a choice of big N is the fact that the sequence xn is Cauchy. So let's do that. Xn is Cauchy. So there exists some big N such that for every k and L bigger than big N, the distance from xk to xl is less than epsilon. Where, again, like maybe this changes to something other than epsilon. We'll see. Cool. And now let's play the same game as we did when we showed that we did something to prove that if xk converges, then each of these converge. Let's see if we can play that same trick. So for any fixed one of these i's and any k and l bigger than big N, I guess there should be a space there. Well, the absolute value of the difference is the square root of the difference. And what does that happened last time to show that that was less than epsilon? What did we do?
Some more things.
Yeah, if we stick in some of a bunch more non-negative things, the whole thing will become bigger. That's less than or equal to the square root of the sum I equals 1 up to n of, well, no, let's use j. So you can't read it at this point anyway. xkj minus x l j. Oh, I lost an L. Squared. But that complicated sum, what is it? That's the distance formula? There's the distance from xk to xl, which by assumption right now is less than epsilon. Oh, hey, cool. Let's just see what happened. Did we consider any epsilon bigger than 0? We came up with the choice of big N. We considered any two things, k and l, bigger than big N, and got the corresponding two terms of this to be less than epsilon, away from each other. So what does that mean about this sequence x up I sub k?
Cauchy.
It's Cauchy. Each of the terms of the sequence is Cauchy. So, by the completeness of the real numbers, what can I conclude? What can you tell me about that sequence?
It converges?
It converges. Since it converges, I can give its limit a name. Let's set xi to be that limit as k goes to infinity, and x be the n tuple consisting of all of those individual limits. What does proposition 2 have anything to say now? I hope it does. Otherwise, I use the wrong /ref.
We converted that.
Where it, in this case, is xk. This sequence converges to x with respect to the L2 metric. And those of you who stay ahead on homework will recall that I had you check that there are two other reasonable metrics on Rn, the taxicab metric and the L infinity metric. Do you think you could use a similar proof on them to get them to be complete? Probably. Yeah, if I'm asking, then it's probably true. Yeah. Rn is complete with respect to the the taxicab or the supreme omnifs. So there's a little bit of abstract stuff. What does it mean for a sequence for a metric space to be complete? One important thing we did with the completeness of Rn is we used it to deduce existence of some limits. So if I can show that a sequence is Cauchy, then I know that that sequence has a limit. One convenient way of showing that a sequence is Cauchy is showing that it's contractive. So consider any sequence xk in a metric space x comma d and a constant c in between 0 and 1. I mean, maybe I'll allow c to be 0. It's a silly property when c is 0. A sequence xk is called contractive with contractive constant c if the distance between two consecutive terms of the sequence is less than or equal to that constant c times the distance between the previous two terms. And I did not actually take the previous two terms. Just as in Math317, every contractive sequence is Cauchy. And it says here homework, but I don't think I actually assigned that as one of the homeworks. I think I was considering it. But it really is, like, if you want to see why, grab the note packet that I think was a group walk in Math316 in which you talked about contractive sequences and use them to detect the square root of 2. Read through exactly that, but replace absolute value of the difference with the distance from x to y. That's all you need to do. Yeah, there it is. See relevant notes from Math316. So here's a cool application. Let's suppose that you want to deduce the existence of a fixed point for some map. So you have some function that sends a metric space to itself. You want to know, is there some input for which this operator sends that point to itself? For instance, your space might be a space of functions, a function space. And your operator might be an operator that has something to do with a differential equation. So you'll rig this operator so that a fixed point is automatically a point that solves a differential equation. If you can show that the operator is that it has this property, then it will follow that that operator has a unique fixed point. So let's try to put it. Let xd be a non-empty complete metric space. Let's let c be a contractive constant. You can allow c equals 0 if you want. I don't think it'll screw up the proof. And f from x to x be a function, which has the property that for every x and y and x, the distance from f of x to f of y is less than or equal to c times the distance from x to y. So it's contractive in that distances get smaller. Everything looks like it's contracting down. Then there exists a single unique point P in X which has f of P is equal to P. So this is like an existence and uniqueness thing, right? So there are only two different things that I'll need to do. I'll need to show that this point exists and that it's unique. Which would you guys like to do first?
Just that it exists.
Let's do existence first. Existence is also the hardest one. Uniqueness is like half a sentence. A full sentence if you want to be grammatically correct. Which apparently I just don't. A map which satisfies this is called a contraction mapping because all the distances contract down. Let's let XD be a metric space. Let's let X be non-empty. Let's let C be a contractive constant. And F from X to X be a contraction mapping with that constant C. I will now set Xn to be a sequence which satisfies the following or constellation. So x1 is just whatever. I don't care what x1 is. Let's set xn plus 1 by the rule xn plus 1 is equal to f of xn. Did I just take advantage of the fact that I assume that this set is non-empty? Yeah, I let something be an element of this set. If you have a function to find out an empty set, does that function have a fixed point?
Yes.
There are no points in this set.
Vacuously.
It's got no points.
Yeah.
A fixed point should be a point in the space. If it's the empty set, there are no fixed points. Also, every point is a fixed point. Okay, but that's not a point. Why is the sequence contracted with constant C? Let's check that. So let's see, to be contracted with constant C, I need that condition to follow. So let's try to compute the distance from x, k plus 2. Let's see, so let's let k be a natural number. Then the distance from xk plus 2 to xk plus 1, let's try to compute that. And let's do it by taking advantage of the constellation. What is x sub k plus 2 the same as? F of xk plus 1. What is xk plus 1 the same as? F of xk. And what do I know about that?
That's less than or equal to C.
Less than or equal to, well, not C, but the thing that I should have written instead of just C.
C times the distance from X to Y.
C times the distance from X to Y, where I, like this typo correction is really, really important. If there were just a less than C there, that would just be the definition, I guess, of what it means for a function on a metric space to be bounded.
Should the x and y be k plus 1 and xk?
Yes. So, does that verify that this sequence is contracted? So, now let's just theorem chase. The theorem that we did not prove says then that this sequence must be
Cauchy.
Cauchy. And what do we know about Cauchy sequences? They converge. I will let P be the limit of this sequence. And now it's all going to come together. I claim that this P is a fixed point for this function. And let's do it by studying the distance between P and f of P.
That lines there being convergent?
Yes. So let's try to do it. So I'll start by considering any epsilon bigger than 0, and I'll go from there. I'll try to show that this difference is less than epsilon. So since p is the limit of this sequence, and I've picked an epsilon bigger than 0, so as p is equal to the limit of x sub k, I know that there exists some big N such that for all little k bigger than big N, well, no, this sequence is indexed by n. It'll be little n bigger than big N. The distance from xn to p is less than epsilon. Then, let's try to do something with this. Let's try to measure the distance from p to f of p by appealing to the triangle inequality. So can I come up with something that is, so right now I know that xn will always be close to p, right? So let's take advantage of the triangle inequality to that. So that'll be less than or equal to the distance from p to, let's say xn plus 1 plus the distance from xn plus 1 to f of p. What's xn plus 1 the same as?
F of x of n.
F of x of n. Let's use that on this one. So that's less than or equal to the distance between p and xn plus 1 plus the distance between f of xn and f of p. I've mismanaged my space. I did skip over that's how I mismanaged. I thought I had enough space, but then I didn't. This n plus 1, is it little n plus 1 bigger than big N?
Yeah.
Yeah, because little n was bigger than big N. So what can you tell me about the distance between p and xn plus 1?
Plus an epsilon.
Less than epsilon. What about the distance between f of xn and f of p?
It's less than c times the distance from x. So x plus 1 to x sub k.
Yeah,
So
so
what are we indexing by?
n, I think. Yeah, you can use k if you want. Distance from p to xn plus 1. That's good because I already know that that's small. Plus c times the distance from xn to p by the fact that this thing is contractive. So that's going to be less than epsilon plus c times epsilon. Do you think I could divide that epsilon by something big enough to get that to just be epsilon? Yeah, I think divide by 1 plus c. So that means the distance from p to f of p is less than epsilon for every positive number epsilon. So what must the distance from p to f of p be? What's the only non-negative number you know that's less than or equal to every positive number? 0. So the distance from p to f of p is equal to 0. And what follows if the distance from p to f of p is 0?
Fixed point.
It's a fixed point. So that gives us existence. And how do you get uniqueness? Well, if you have two different fixed points, p and q, then the distance from p to q must be less than or equal to that c times the distance from f of p to f of q. So the distance from p to q is less than or equal to a number that's less than 1 times the distance from p to q. If you have a positive number and multiply it by a number that's less than 1, do you get a number that's the same? No. So there's the contradiction. And that was fast, but like I'm a minute over right now. I can say these things again slower at the start of next time, if there is demand. Well, possibly just more organized, more well organized at the start of next time. Cool. So, I'll tell you what the plan is for next time. So the next thing that I want you guys to do is I want you guys to prove that Newton's method of approximating solutions to equations works. And so it'll be a group work about Newton's method. Cool. I'm going to stop this.